Out there, beyond the blue of our sky, lies a vast ocean of stars, quiet, endless, and waiting to be understood. Every speck of light you see at night is a story still unfolding, a piece of the universe whispering across time. What makes the stars shine? How do galaxies take shape and drift through the dark? And could there be other worlds, spinning around distant suns, wondering the same thing about us? Tonight, let's drift together through space and time, gently uncovering what the universe still keeps hidden. If you enjoy these cosmic journeys, give this a like and subscribe. It helps us keep exploring the unknown, one wonder at a time. Now, settle in. Let's look up and begin. A star is a vast, glowing sphere of gas, mostly hydrogen and helium held together by its own gravity. Our sun is the nearest of these, the warm and steady source of light that makes life on Earth possible. When night falls, the other stars reveal themselves as quiet points scattered across the dark. They look small because of distance, yet each one is a sun of its own. People long ago grouped the brightest of them into familiar patterns, naming constellations and smaller shapes called asterisms. Modern astronomy continues this work, gathering precise catalogs that record the position and brightness of each star. Though the observable universe may hold more than a septillion stars, a number almost beyond imagination, only about 4,000 can be seen with the naked eye, all within our Milky Way. Every star begins its life in a nebula, a huge, cold cloud of gas and dust adrift in space. Gravity slowly draws parts of the cloud inward, compressing and heating the material until the pressure becomes great enough to ignite nuclear fusion. The star is born in light and heat. Inside its core, hydrogen atoms fuse into helium, releasing energy that pushes outward while gravity pulls inward. For most of a star's life, this balance keeps it shining. The brightness we see is the result of this steady struggle between pressure and gravity. How long a star lives depends on its mass. Small stars burn their fuel slowly and can last billions of years. Larger ones consume it rapidly and die young. When the fuel in the core runs out, fusion stops. The star begins to collapse under its own weight. Some end quietly as white dwarfs, dense, fading embers the size of a planet. Others explode as supernovae, scattering their outer layers into space. The most massive collapse entirely, forming neutron stars or black holes where gravity becomes inescapable. These deaths are not an ending for the universe, but part of its renewal. During fusion and in the violent moments of a supernova, stars create almost all elements heavier than hydrogen and helium. The oxygen we breathe, the iron in our blood, the carbon in our cells. The dust and gas they expel mix with interstellar clouds, forming the raw material for new stars and planets. Each generation of stars carries within it the remains of those before. In a real sense, everything we are was once part of a star. By studying how stars shine and move, astronomers can learn their age, distance, and chemical makeup. They examine a star's light through instruments that separate it into a spectrum, a rainbow crossed by thin, dark lines. These lines reveal which elements are present in the star's atmosphere, since each element absorbs light at specific wavelengths. By comparing spectra, scientists discovered that not all stars are the same. Some are hot and blue, others cool and red. The system for classifying them began in the 19th century and was refined by Annie Jump Cannon in the early 1900s into the familiar categories we still use today. Stars often live in company. Two stars bound by gravity form a binary system, circling a shared center. Their pull on one another changes their brightness and motion in ways that can be measured from Earth. Some systems hold 3 or more stars, and many belong to larger groups called clusters, families born from the same cloud. Our sun, though solitary now, may once have had siblings that drifted away long ago. Humanity's relationship with the stars stretches back to the first nights of curiosity. Ancient observers noticed that some points of light never changed their positions, while others, the wandering stars, now known as planets, moved among them. To bring order to the sky, people drew imaginary lines between bright stars, forming constellations that carried myths and meaning. The stars became guides for travel and agriculture, marking the passage of seasons and shaping calendars. Records of these efforts reach deep into history. Egyptian star charts carved around 1500 BCE traced the heavens with remarkable care. Babylonian astronomers created early catalogs of stars more than 3,000 years ago. In Greece, scholars like Hipparchus mapped over 1,000 stars and discovered that the sky itself slowly shifts over centuries. Chinese astronomers recorded new stars that suddenly appeared supernovae and noted that the heavens were not fixed. The great explosion of the year 1006 lit their sky so brightly it could cast shadows at night. During the Middle Ages, Islamic astronomers carried this work forward. They built observatories, named countless stars, and described objects we now recognize as galaxies. Abd al-Rahman al-Sufi's Book of Fixed Stars, written in the 10th century, included the Andromeda Nebula long before telescopes existed. Others, like al-Biruni, realized that the hazy path, the Milky Way, was made of innumerable tiny stars. In Europe, discoveries followed. Tycho Brahe observed new stars that proved the sky could change. Giordano Bruno proposed that the stars were suns like ours, perhaps with their own planets. By the 17th century, most astronomers agreed. Isaac Newton reasoned that if the star's gravity were spread evenly through infinite space, the universe would remain balanced rather than collapse. Observers like Edmund Halley noticed that some stars shifted position since ancient times evidence they were truly in motion. William and John Herschel counted stars across the sky and found that their numbers increased toward the band of the Milky Way, mapping the rough shape of our galaxy. In the 19th century, new tools transformed astronomy. Fraunhofer and Secchi studied starlight with prisms and saw those distinctive absorption lines. They realized each star had its own spectral fingerprint. Later, Friedrich Bessel measured the distance to a star 61 Cygni by detecting a tiny shift in its position as Earth moved around the Sunday. It was about 11 light years away, confirming that the stars were unimaginably far. Astronomers soon found that some stars moved in pairs too close to separate, even with a telescope. By watching the way their spectral lines shifted back and forth, Edward Pickering identified the first spectroscopic binary. Observers like Struve and Burnham spent decades charting these systems, allowing the calculation of stellar masses and orbits with growing precision. Photography then added speed and accuracy, letting astronomers record and compare the brightness of stars night after night. Karl Schwarzschild showed that a star's color could reveal its temperature: blue for hotter, red for cooler. Michelson later used an interferometer to measure a star's diameter directly, a feat once thought impossible. Around the same time, the Hertzsprung-Russell diagram brought clarity to stellar life cycles, linking color, brightness, and evolution in a single picture. Cecilia Payne-Gaposchkin's work in 1925 changed our understanding entirely, proving that stars are mostly hydrogen and helium, not heavier matter, With the rise of quantum physics, astronomers could explain the details of these spectra and describe stars as vast nuclear engines, each one a laboratory of light and time. From ancient carvings to modern telescopes, the study of stars has been one long conversation across centuries. Each generation added its voice, refining what the previous one only glimpsed. What began as patterns in the night sky has become a science that reaches across the universe, showing that the same laws of nature guide both the stars above and the life below. Most of what we know about stars comes from those close enough to study in detail within our own Milky Way and its small companion galaxies, which together form a neighborhood called the local group. Astronomers have spent generations building vast catalogs that record the positions, brightness, and colors of stars across the sky. Beyond our galaxy, a few stars stand out even at enormous distances. Some of these are variable stars, like Cepheids, which rhythmically brighten and dim. Their predictable light changes allow astronomers to measure distance across space. Cepheid stars have been observed in galaxies like M87 and M100, far out in the Virgo cluster, giving us a way to gauge the scale of the universe. There are rarer and more extraordinary sights. Occasionally, gravity itself acts as a natural telescope. When a massive galaxy lies between us and a faraway star, its gravity can bend and magnify the distant starlight. This is known as gravitational lensing, an effect predicted by Einstein's theory of relativity. Through this cosmic alignment, astronomers once observed a single distant star nicknamed Icarus, whose light had traveled nearly 9 billion years to reach us. That faint shimmer carried the story of a time when galaxies were still forming, showing that even the most fragile light can survive the immensity of space and time. The way humans see the stars has always been shaped by imagination. Long before telescopes, people noticed that some stars seemed to form shapes in the sky, animals, heroes, and symbols of the forces of nature. These imagined patterns became constellations. Among them, 12 appeared along the sun's yearly path across the heavens, a route called the ecliptic. Those 12 constellations became the foundation for astrology, where celestial patterns were believed to reflect human destiny. Though we no longer see the sky in quite that way, these constellations remain part of the language of astronomy. Over time, the brightest stars gain names, many from Arabic and Latin, reflecting the cultures that preserved and advanced astronomy through the Middle Ages. Naming was not only practical but also a form of storytelling. Each star carried a history, a myth, or a god's name. The Greeks noticed that not every bright object stayed fixed in place. Some wandered slowly against the background of stars. They called them planetes, meaning wanderers. These became the planets, and each was linked to a deity. Mercury with Hermes, swift messenger of the gods. Venus with Aphrodite, the goddess of love. Mars with Ares, god of war. Jupiter with Zeus, ruler of Olympus. And Saturn with Cronus, the ancient god of time. Uranus and Neptune, discovered centuries later through telescopes, continued that tradition of divine names. By the early 1600s, as astronomy turned toward precision, star naming became systematic. The German astronomer Johann Bayer introduced a clever way to label stars using Greek letters and constellation names. For instance, Alpha Centauri marks the brightest star in Centaurus. Later, John Flamsteed refined this approach, ordering stars by their position in the sky, what astronomers call right ascension. the celestial version of longitude. His work, published in Historia Coelestis Britannica in 1712, became the Flamsteed system, still in use today. In modern times, the task of naming celestial bodies belongs to the International Astronomical Union, or IAU. Within it, the Working Group on Star Names maintains an official list of approved names, despite what some companies claim when selling official star names. Only those recognized by the IAU are considered valid. Consumer protection agencies have even warned against such commercial naming schemes, reminding the public that the stars belong to everyone, not to those who can afford to buy them. When describing stars, astronomers often measure them relative to the sunday. Instead of using huge numbers, they compare a star's mass, size, or brightness as multiples or fractions of solar values. In 2015, the IAU established standard solar measures to use as reference points. The sun's mass, for example, is defined as about 2 × 10⁻30 kilograms, a number so large that comparison becomes essential. Distances within our solar system are measured in astronomical units, or AUs, each representing the average distance between Earth and the Sun, roughly 150 million kilometers, now defined with exact precision. Stars themselves are born in immense clouds of cold gas and dust called molecular clouds. Despite their vast size, these clouds are incredibly thin, far emptier than any vacuum on Earth, yet dense enough for gravity to work slowly over millions of years. Most of the material is hydrogen, with about a quarter helium and traces of heavier elements. The Orion Nebula, visible as a faint glow in the night sky, is one of the nearest examples of such a stellar nursery. Within these clouds, new stars often form in clusters from a few dozen to hundreds of thousands. The most massive among them shine so brightly that their radiation ionizes the surrounding hydrogen, creating glowing shells of gas called H2 regions. Over time, their intense light and stellar winds can break apart the very clouds that gave them birth, stopping further star formation nearby. Once born, a star spends the majority of its life in what astronomers call the main sequence, quietly converting hydrogen into helium in its core through nuclear fusion. But not all stars follow the same journey. Those with less than half the sun's mass burn fuel slowly and evenly, circulating material throughout their interiors. They never swell into red giants. Instead, they eventually become compact white dwarfs made of helium. None of these faint red dwarfs has yet completed its life. The universe itself is still too young for that. Stars, like our sun, live longer, but end differently. When the hydrogen in their cores runs out, fusion shifts outward, causing their outer layers to expand. They grow into red giants, glowing cooler and larger, before gently shedding their envelopes into space. The remaining core contracts into a white dwarf, a dense ball of carbon and oxygen, surrounded by a faintly glowing shell of gas, a planetary nebula. More massive stars, up to about 8 times the sun's mass, evolve faster. They spend a long period in what astronomers call the red clump, a stable phase of helium burning. When their fuel is gone, they too end as white dwarfs, though they live shorter, more turbulent lives. The differences among stars, how they shine, how long they last, and how they die, all trace back to one simple factor: how much mass they were given at birth. From that single measure, the universe writes 1,000 different fates in the language of light. Massive stars, those with more than about 8 times the mass of the sun, live intense, and short lives. They burn through their hydrogen quickly, fusing heavier and heavier elements as they age. In just a few million years, they swell into supergiants, bright, enormous stars whose power comes at the cost of longevity. When fusion can no longer support their weight, their cores collapse and the outer layers explode outward as supernovae. These explosions scatter the newly created elements, carbon, oxygen, iron, across space, seeding the next generation of stars and planets. Every star's story begins deep inside a giant molecular cloud, a cold, dark region filled with thin gas and dust. Within these clouds, small areas sometimes become slightly denser than their surroundings. Gravity then begins to take over, pulling material inward. This process, called gravitational instability, can start for many reasons, perhaps from shock waves left by other exploding stars, radiation from nearby massive stars, or even the collision of galaxies that triggers a burst of new star formation. As a region collapses further, it reaches a threshold known as the gene's instability, where gravity completely dominates. The gas fragments into smaller pockets called Bach globules, tiny, dense spheres of dust and gas, each one a potential future star. As gravity squeezes these globules, they heat up. At the center of each, a new object forms, a protostar, glowing faintly from the energy of contraction. Around it, a flat disk of gas and dust called a protoplanetary disk spins slowly, the birthplace of future planets and moons. This early stage of a star's life can last millions of years. For a sun-like star, about 10 million years pass before nuclear fusion begins. For smaller stars, the process takes longer, sometimes hundreds of millions of years. During this time, young stars, known as T Tauri stars, if smaller than twice the sun's mass, or Herbig stars, if larger, often release powerful jets of gas along their poles. These jets, bright and narrow, help the star shed excess spin and clear away surrounding gas. Where these streams strike nearby material, they create glowing patches called Herbig-Haro objects, tiny signs of stellar youth scattered across nebulae. As the protostar continues to shrink and warm, it follows a path known as the Hayashi track. Its surface temperature stays nearly constant while its brightness fades. When nuclear fusion finally ignites in the core, the balance between gravity and pressure stabilizes, and the star enters the main sequence, the long, steady phase of its life. Most stars are not born alone. The collapsing cloud often splits, forming two or more stars that share the same origin. These pairs, called binary systems, can circle each other closely or drift far apart. Over time, interactions within young clusters rearrange these systems. Some binaries are pulled apart by the gravity of neighbors, while others tighten into closer orbits. This quiet dance determines much of how stars evolve and how they eventually die. Once settled on the main sequence, a star spends about 90% of its lifetime steadily fusing hydrogen into helium in its core. The Sun, for instance, has been doing this for more than 4 billion years. Its brightness has slowly increased by about 40% since its birth, as fusion becomes more efficient and the core grows hotter. During this time, all stars produce a steady stream of charged particles called stellar wind. For stars like the Sun, this outflow is gentle, but massive stars can lose huge amounts of mass through these winds, shedding more than half their material before they even leave the main sequence. The pace of a star's life depends mainly on its mass. The Sun is expected to live for about 10 billion years. In contrast, massive stars burn furiously and die after only a few million years, while small red dwarfs, with a fraction of the sun's mass, can shine quietly for trillions of years, far longer than the universe has existed so far. These faint red stars will be the last to burn when everything else has faded. Another factor shaping a star's evolution is metallicity, the proportion of elements heavier than helium within it. Astronomers use the word metals for all such elements, and the amount a star contains affects how it shines, how strong its winds are, and how quickly it ages. The first stars in the universe, known as population 3 stars, contained almost no metals at all. Later generations, called population 2 and then population 1, formed from gas enriched by earlier stars. Each new wave carried more of the heavy elements that make up planets and life itself. As stars like the sun exhaust their hydrogen, fusion shifts from the core to a thin shell around it. The outer layers expand, and the star cools and reddens. It becomes a red giant. The core contracts into dense helium while the surface grows vast and luminous. Eventually, the star begins burning helium into carbon and oxygen. The sun will reach this stage about 5 billion years from now, swelling until its radius nearly equals Earth's current orbit. In stars slightly less massive than the sun, the helium core becomes so dense that the atoms inside act more like a single compressed fluid than ordinary matter. When fusion starts again, it does so suddenly in a helium flash, releasing enormous energy and shrinking the star back to stability. It then settles on the horizontal branch of the Hertzsprung-Russell diagram, shining steadily once more. More massive stars experience this transition more smoothly, burning helium calmly in what is called the red clump stage, before moving on. When helium in the core is gone, fusion continues in surrounding shells, and the star swells again, entering the asymptotic giant branch. Here, its surface pulses, growing brighter and dimmer as waves of heat drive material into space. These thermal pulses mix the star's layers and send carbon and oxygen outward, forming the seeds of future worlds. Over time, much of the star's mass drifts away, forming a delicate glowing shell known as a planetary nebula. What remains at the center is a white dwarf, the final ember of a once living star. The gas and dust it leaves behind spread through the galaxy, enriching the interstellar medium. From that enriched material, new clouds collapse, new stars ignite, and new planets form. For the largest stars, those with more than 9 times the mass of the sun, the path diverges. They swell into brilliant blue and then red supergiants, their lives measured not in billions of years but in millions. When their fuel is finally gone, their cores collapse in an instant, triggering supernovae that light up the universe and mark the birth of neutron stars, or black holes. In their death, they give back everything they ever made, ensuring that the universe remains a place of endless renewal. The most massive stars, those above about 40 times the sun's mass, follow a different path. Instead of swelling into red supergiants, they shed material so quickly that their outer layers peel away. What remains is a bare, hot core known as a Wolf-Rayet star. Its light carries strong emission lines, signatures of elements like carbon, nitrogen, and oxygen that have been dredged up from deep inside. Powerful winds strip these stars further, exposing hotter layers and speeding their end. When helium runs out in a massive star's core, gravity tightens its grip again, temperatures rise, and new fusion stages begin. Carbon, then neon, then oxygen, then silicon. Each stage burns faster than the one before. The star develops an onion-like structure, hydrogen in the outer shell, helium beneath it, then deeper shells where heavier elements fuse. This chain stops at iron. Iron nuclei are so stable that fusing them uses energy instead of releasing it, so there is no more pressure to counter gravity. The star is out of options. Some very bright, unstable stars show trouble even earlier. Luminous blue variables can erupt, throwing off large amounts of mass and brightening for months or years. These events look like supernovae from a distance, but do not destroy the star, so they are sometimes called supernova imposters. Eta Carinae is the best-known case. In the 19th century, it flared until it became one of the brightest objects in the sky, then faded again, wrapped in clouds of gas and dust. Lower mass stars approach their endings more gently. As the core contracts, radiation pushes on the outer layers and lifts them away, forming a delicate shell of gas called a planetary nebula. The star's leftover core becomes a white dwarf, an Earth-sized ember made of matter in an unusual state called electron-degenerate matter. In this state, pressure comes from electrons packed so tightly that they resist further compression. White dwarfs cool slowly for billions of years, growing dimmer until they become cold, dark remnants. For massive stars, the final act is sudden. When the iron core grows heavier than about 1.5 times the sun's mass, it can no longer bear its own weight. Electrons are crushed into protons, creating neutrons and a burst of neutrinos. The core collapses at high speed and then rebounds. A shock wave races outward, tearing the star apart in a supernova. For a brief time, the explosion can outshine an entire galaxy. The outer layers blast into space and form glowing remnants like the Crab Nebula. The collapsed core survives as something new. If its mass is modest, it becomes a neutron star, a city-sized sphere of neutrons, incredibly dense and often spinning fast. Some sweep beams of radiation across space and appear as pulsars. If the core is too heavy, gravity wins completely. A black hole forms, a region from which not even light can escape. These violent endings enrich space. The ejected gas carries carbon, oxygen, iron, and many heavier elements, which mix with interstellar clouds. Later, those clouds collapse into new stars and planets. Without this recycling, rocky worlds could not form. The winds of massive stars and the shock waves of supernovae also reshape their surroundings, compressing some regions to trigger new star birth and blowing others apart to halt it. The story becomes more complex in binaries. Many stars orbit a partner, and when one star swells into a red giant, its outer layers can spill onto the other. This mass transfer creates a range of phenomena. Contact binaries share a common envelope. Cataclysmic variables flare as matter falls onto a white dwarf. In some pairs, a white dwarf steals enough material to ignite a runaway nuclear reaction and explode as a Type Ia supernova, a standard candle for measuring cosmic distances. Mass exchange can also produce blue stragglers, stars that look younger and hotter than their neighbors, solving the puzzle by revealing that they are the products of mergers or transfers. Sometimes, the donor star ends up looking older and lighter, while the accreting star looks younger and heavier. This is the Algol paradox. Because binaries are common, roughly half of Sun-like stars are in pairs, and the fraction is even higher for massive stars. Binary evolution is central to understanding how stars live and die. Some astronomers argue that the stripped, evolved giants we see luminous blue variables, Wolf-Rayet stars, and certain supernova progenitors often owe their shapes and fates to these exchanges. Stars rarely wander alone across the universe. They gather in galaxies along with gas and dust. A large spiral like the Milky Way holds hundreds of billions of stars. Across the observable cosmos, there may be more than 2 trillion galaxies. In crowded clusters of galaxies, a significant share of the total light can come from loose stars drifting between galaxies, no longer bound to any one system. Many stellar systems hold 2 or more stars. Triples and higher-order multiples are usually arranged in a stable hierarchy. Close pairs orbit each other, and that pair orbits another star farther out. Even larger gatherings are star clusters. Open clusters are loose and young, with dozens to thousands of stars born from the same cloud. Globular clusters are dense and ancient, holding hundreds of thousands of stars in a compact sphere. Because all stars in a cluster form together, they share age and chemistry, allowing astronomers to trace how stars evolve. Multiplicity depends on mass. Among the hottest, most massive O and B stars, about 4 in 5 belong to multiple systems. Among red dwarfs, which are small and common, only about a quarter have companions. Since red dwarfs make up the great majority of stars in the Milky Way, most stars in our galaxy are likely solitary. Yet the picture at birth may be different. A 2017 study of the Perseus molecular cloud suggested that newborn stars often form in pairs, and many may start as binaries before some systems drift apart. Distances between stars are vast. The nearest star beyond the Sun is Proxima Centauri, about 4.24 light-years away, roughly 40 trillion kilometers. At the speed of a low Earth orbit spacecraft, the trip would take on the order of 150,000 years. Such spacing is typical in the thin disks of galaxies. In the dense cores of galaxies and inside globular clusters, stars are much closer together. In the extended halos around galaxies, they can be far more widely spaced. Because of these wide separations, direct collisions between stars are rare. In crowded regions, cluster cores, and galactic centers, they happen more often. There, interactions can lead to mergers or close passes that strip mass. Blue stragglers in clusters likely come from such collisions or mass transfers, which refresh a star's fuel supply and make it appear bluer and younger than others of the same age. A star's initial mass is the master key. It sets brightness, size, temperature, how quickly fuel is burned, and how the star will end white dwarf, neutron star, or black hole. Most stars we observe are between 1 and 10 billion years old, though a few push toward the beginning of cosmic time. One notable example is HD 140283, the Methuselah star, with an age estimate around 14.5 billion years, but with nearly a billion years of uncertainty. Within those margins, it remains consistent with the universe's age, measured at about 13.8 billion years. The heavier the star, the shorter its life. Massive stars burn through their fuel quickly and perish after only a few million years. Small red dwarfs sip fuel slowly and can last for tens to hundreds of billions of years, far longer than the universe has existed so far. Long after brighter stars have faded, these quiet embers will still shine, carrying the story of stellar evolution into the deep future. When new stars form in the Milky Way today, they are built mostly from hydrogen and helium, about 71% hydrogen, 27% helium, and only a trace of heavier elements. Astronomers call all these heavier ingredients metals, and they often measure a star's metallicity by the amount of iron in its outer layers. Iron is easy to detect in a star's spectrum, and its abundance tells much about the star's past. Metal-rich stars are more likely to host planets, while ancient, metal-poor stars trace back to the early universe. Some stars contain almost no heavy elements. One record holder, HE 1327 to 2326, has only about 1/200,000th as much iron as the Sunday. Others go the opposite way. Mu Ra has nearly twice as much iron, and 14 Hercules, known to have planets, has almost 3 times the Sun's iron content. A few stars show odd chemical patterns altogether. These chemically peculiar stars contain unusual amounts of chromium, manganese, or rare earth metals, hints of complex processes inside them. Cooler stars, including our Sun, sometimes have conditions in their outer layers that allow molecules, atoms, bound together to form briefly before being torn apart again. But no matter how complex their chemistry, every star beyond the Sun appears to us as a single point of light. Their twinkling is caused not by themselves, but by the movement of Earth's atmosphere. Only the Sun, close enough to us, appears as a disk and fills our days with light. The largest star visible from Earth, R Doradus, spans just 0.057 arcseconds in the sky, far too small for human eyes to discern. To study stars more closely, astronomers rely on indirect methods. Interferometry combines the light of multiple telescopes to simulate a single giant mirror, allowing precise measurement of stellar diameters. Another method, called occultation, times exactly how long it takes for a star to vanish behind or reappear from behind the moon, using that instant to estimate its size. The true range of stellar sizes is vast. At the smallest end are neutron stars, collapsed remnants only a few tens of kilometers across, but heavier than the Sunday. At the opposite extreme are red and blue supergiants like Betelgeuse, which could swallow hundreds of suns across its surface, yet has a low average density, more like a thin fog than solid matter. Stars move through space in complex ways. Their motion reveals clues about their birthplaces and the structure of the galaxy. Astronomers describe these motions using 2 main measures. Radial velocity shows how fast a star moves toward or away from us, detected by the Doppler shift in its light. Proper motion describes how it drifts sideways across the sky, measured in thousandths of an arcsecond per year. By combining these with distance, scientists calculate a star's true speed through the galaxy. Nearby stars tend to show the largest proper motions and are the easiest to track precisely. Younger stars, called population I, usually follow smooth, circular paths around the Milky Way. Older population II stars move faster and on more tilted or elongated orbits, showing that the galaxy has thickened and changed shape over billions of years. Sometimes astronomers can trace a group of stars back to a single birthplace, a giant cloud that once gave rise to them all. These family groups are known as stellar associations, bound not by gravity, but by shared origin. Deep inside each star, invisible forces shape its behavior. Magnetic fields, born from the motion of hot plasma in the interior, stretch outward through the surface and far into space. The process works like an enormous dynamo. As charged particles swirl and twist, they generate magnetic power. The strength of this field depends on the star's rotation and structure. Rapidly spinning stars have more intense fields and more activity. On their surfaces, magnetic forces create dark patches called star spots, cooler regions where energy flow is suppressed. Huge arcs of plasma, known as coronal loops, follow the magnetic lines up into the outer atmosphere. Occasionally, tangled magnetic lines snap and reconnect, releasing powerful stellar flares that hurl energy and particles into space. Young stars, which rotate quickly, are stormy and unpredictable. Over time, the magnetic field itself slows their spin by interacting with the stellar wind. As they age, their rotations and tempers calm. Even our sun goes through cycles of activity and rest. Its sunspots and flares rise and fade roughly every 11 years. But there have been long quiet periods too. During the Maunder Minimum, from the mid-1600s to the early 1700s, the sun was almost spotless for 70 years, a silence still studied today. Stars differ not only in age and activity, but in sheer scale. Some are smaller than half the sun's mass. Others exceed 200 suns. One of the true giants, Eta Carinae, has between 100 and 150 times the sun's mass and burns so fiercely that it sheds vast clouds of gas. Such titans live only a few million years before exploding or collapsing. Evidence suggests an upper limit to stellar mass today, around 150 suns, because radiation pressure pushes material away before a star can grow larger. Yet in certain regions, like the R136 cluster in the Large Magellanic Cloud, some stars appear to exceed that limit. Astronomers think they may be the products of mergers, two massive stars colliding and combining into one even larger. The first stars that ever existed, born soon after the Big Bang, may have been far greater still. With no heavy elements to trap heat, they could grow unchecked, perhaps reaching 300 solar masses. These primordial giants, called population 3 stars, lived short, brilliant lives. Their explosions created the first heavy elements, the seeds from which planets, chemistry, and life would eventually emerge. In 2015, astronomers reported possible traces of such ancient stars in a remote galaxy known as Cosmos Redshift 7. Its light began its journey when the universe was still young, a faint echo from the dawn of starlight itself. At the smallest end of the stellar scale lies one of the faintest true stars ever found, 2 Mass J 523 1403. It has only about 80 times the mass of Jupiter, barely enough to sustain nuclear fusion in its core. For stars with a makeup like the Sun's, the minimum mass for fusion is roughly 75 Jupiters. If a star has very few heavy elements, what astronomers call low metallicity, the limit rises slightly to around 87 Jupiters, or about 8% of the Sun's mass. Below that boundary, fusion never starts, and an object becomes a brown dwarf, something between a planet and a failed star. A star's mass shapes everything about it, including its surface gravity. Giant stars, swollen to enormous size, have gentle gravity at their outer layers, while compact remnants like white dwarfs or neutron stars crush matter with unimaginable force. This gravity leaves subtle clues in a star's spectrum. The stronger it is, the broader the absorption lines appear, spreading out under the immense pull of the star's surface. Rotation adds another layer of complexity. Astronomers can measure a star's spin either by analyzing patterns in its spectrum or by watching the drift of star spots across its face. Young stars often rotate at astonishing speeds, more than 100 kilometers per second at the equator. The hot blue star Achernar spins even faster, around 225 kilometers per second. This speed makes its shape bulge outward, so its equator is more than half again, as wide as its poles. Any faster, and it would tear itself apart. By contrast, our sun turns slowly, taking about a month to complete one rotation, moving less than 2 kilometers per second at its equator. Over time, magnetic fields and stellar winds act like brakes, slowing a star's spin as it ages. For dead stars, rotation takes a strange turn. Compact remnants should in theory, spin rapidly due to conservation of angular momentum, yet much of their spin is lost before collapse, carried away by powerful winds. Some, however, still turn at breathtaking rates. The pulsar in the Crab Nebula spins about 30 times every second, a rhythm so steady it rivals the precision of atomic clocks. Even so, it gradually slows as it radiates energy into space. A star's temperature tells another part of its story. For main sequence stars, those in the long, stable phase of burning hydrogen into helium temperature depends mainly on the energy produced in the core and the star's size. Astronomers estimate it using the color index, a measure of how bright the star looks through different filters. The result, called the effective temperature, describes how hot a perfect blackbody would need to be to shine as the star does. The true surface temperature varies from star to star. Massive blue stars can exceed 50,000 Kelvin, while red giants glow softly at around 3,600. The sun sits in the middle, near 5,800 Kelvin. Inside, the heat rises sharply toward the core, where it reaches millions of degrees. That heat governs which atoms are ionized, stripped of electrons, creating unique fingerprints in the spectrum. These absorption lines, along with brightness and color, form the foundation of stellar classification. The energy that keeps stars shining comes from nuclear fusion, where lighter elements combine into heavier ones, releasing vast amounts of energy as gamma rays. This energy slowly moves outward, transforming into visible light and other kinds of radiation. The outer layers of a star determine what color we see: blue for the hottest, yellow for stars like the sun, and orange or red for cooler ones. But stars emit far more than visible light. Their energy stretches across the electromagnetic spectrum from long, lazy radio waves to fierce bursts of ultraviolet X-rays and gamma rays. Each wavelength reveals a different part of the star's structure and behavior. By studying starlight, astronomers can uncover remarkable details: a star's temperature, chemical makeup, surface gravity, spin, even its mass and age. When a star's distance is known, often through parallax measurements, its true brightness or luminosity can be calculated. That, in turn, reveals its size and structure through models of stellar physics. Binary systems make this process more exact. By watching how paired stars orbit each other, astronomers can weigh them directly. In other cases, a phenomenon called gravitational microlensing, where a star's gravity bends and amplifies the light of another star behind it, can also provide a way to measure mass. A star's luminosity is the total energy it emits each second, determined mostly by its surface temperature and radius. But stars are rarely uniform. Some, like Vega, spin so quickly that their poles become hotter and brighter than their equators. Others display dark star spots, cooler areas where magnetic fields block energy. On giant stars, these spots can grow to enormous size, while the edges of the disk appear dimmer than the center, an effect called limb darkening. Small, active red dwarfs, such as UV Ceti, may erupt with colossal star spots that reshape their brightness entirely. The brightness we see from Earth is called apparent magnitude. It depends on the star's true luminosity, distance, and how much interstellar dust dims its light. Astronomers also use absolute magnitude, the brightness a star would have if it were exactly 10 parsecs, or about 33 light-years away. The modern system for classifying stars by their spectra began in the early 20th century. At first, letters from A to Q were used to describe the strength of hydrogen lines. which were thought to increase steadily with temperature. Later, astronomers discovered the pattern was more complicated. The hydrogen line actually reaches its maximum strength at about 9,000 Kelvin, then weakens again at higher temperatures. The system was later rearranged into its modern form, grouping stars mainly by temperature. Stars today are classified by a simple letter system that runs from O, the hottest, to M, the coolest. The sequence goes O, B, A, F, G, K, and M, with cooler stars and brown dwarfs placed into new categories, L and T. Each class is divided into 10 steps, numbered from 0 to 9. Our Sun is a G2 star, moderately warm and yellow. At the extreme hot end, the system becomes uncertain, since stars as hot as type O0 or O1 may not actually exist. Stars are also grouped by size and surface gravity, shown through differences in their spectral lines. Main sequence stars like the Sun belong to class V. Giants are class 3, hypergiants are class 0, and white dwarfs are sometimes placed in class 7. On a chart of brightness versus temperature, main sequence stars form a narrow band across the center, a record of stellar life. Extra symbols refine these types. The letter E marks emission lines, M shows unusually high metal content, and VAR indicates that the star's spectrum changes over time. White dwarfs use their own code starting with D, followed by letters such as DA, DB, or DC to show which spectral lines dominate, and a number for temperature. Not all stars shine steadily. Variable stars change in brightness for many reasons. Pulsating variables expand and contract rhythmically, brightening and dimming over cycles from minutes to years. Famous examples like Cepheids are used to measure cosmic distances. Others, called eruptive variables, flare up because of violent bursts of energy or gas. These include young protostars and massive Wolf-Rayet stars. More explosive types, known as cataclysmic variables, experience sudden outbursts, novae, or even supernovae. In some binary systems, a white dwarf draws gas from a companion until enough hydrogen builds up to ignite in a runaway reaction. The result may be a bright nova, or, if stronger, a type 1 supernova. Brightness can also vary because of geometry. In eclipsing binaries, one star passes in front of another, blocking its light. Algol is a well-known case. It dims every 2.87 days as one star hides the other. Inside a stable star, opposing forces remain in delicate balance. Gravity pulls inward, while pressure from the hot gases pushes outward. This steady state, called hydrostatic equilibrium, keeps the star from collapsing or expanding. The pressure is greatest near the core, where temperatures exceed 10 million Kelvin, hot enough for hydrogen to fuse into helium. Each fusion reaction releases energy as gamma rays, which bounce off countless particles inside, slowly losing energy as they travel outward. On the main sequence, hydrogen fuses into helium for millions or billions of years, keeping the star stable. A second balance, thermal equilibrium, ensures that energy leaving the core equals the energy produced within it. This even flow keeps the star's temperature and brightness steady. How energy moves through a star depends on its structure. In some layers, light carries the energy by radiation. In others, hot gas moves it by convection, where warm plasma rises and cooler plasma sinks. Massive stars have convective cores and radiative outer layers. The Sun is the reverse, with a radiative core and a convective outer zone. Small red dwarfs are fully convective, mixing their gas so thoroughly that they never build a dense helium core. The visible surface of a star is the photosphere, the thin layer where light finally escapes into space. This is where dark star spots appear, caused by magnetic activity. Above it lies the chromosphere, a layer of rising jets called spicules and bursts of solar flares. Higher still is the transition region, where the temperature jumps suddenly, and beyond that, the corona, a vast halo of superheated plasma stretching millions of kilometers outward. Though much hotter than the surface, the corona glows faintly because its gases are thin, and it is usually visible only during a total solar eclipse. From the corona flows the stellar wind, a stream of charged particles that spreads far into space. Around our sun, this flow creates a bubble called the heliosphere, reaching well beyond Pluto's orbit. The power behind it all is the conversion of mass into energy. When light atoms fuse into heavier ones, a tiny fraction of their mass disappears, turning into energy as described by Einstein's equation of mass-energy equivalence. The type of fusion depends on the star's mass. Hydrogen burning is extremely temperature sensitive. Hotter cores fuse fuel faster. Core temperatures range from about 4 million Kelvin in small red stars to 40 million in massive blue ones. The sun's core, at roughly 16 million Kelvin, powers itself mainly through the proton-proton chain. In far larger stars, higher temperatures ignite heavier elements, in turn neon, oxygen, and silicon, until fusion reaches iron, the most stable nucleus. Beyond that, no more energy can be released. The fire goes out, and gravity begins to pull the star toward its inevitable collapse. A galaxy is like a vast cosmic city made of stars, clouds of gas and dust, the faint remains of long-dead suns, and a mysterious form of invisible matter called dark matter. All these parts are bound together by gravity, the quiet force that shapes the structure of the universe. Galaxies come in an astonishing range of sizes. Some contain only a few hundred stars. Others hold hundreds of trillions. A typical galaxy may include around 100 million, each orbiting a common center of gravity. Yet the visible stars, gas, and dust are only a small part of the story. Most of a galaxy's true mass is hidden, locked in dark matter that cannot be seen directly but reveals itself through its pull on everything else. At the hearts of many galaxies lie supermassive black holes, regions so dense that not even light can escape their grasp. Astronomers classify galaxies by their shape. Smooth, rounded systems are called elliptical galaxies. Flat, rotating disks with sweeping arms are spiral galaxies, like our own Milky Way. Others are irregular, with chaotic forms caused by collisions or gravitational distortions. Across the observable universe, there may be between 200 billion and 2 trillion galaxies, each spanning from a few thousand to hundreds of thousands of parsecs, or up to about 300,000 light-years across. The distances between them are immense, often millions of parsecs, meaning millions of times the distance that light travels in a single year. Our Milky Way measures roughly 27,000 parsecs, or about 87,000 light-years in diameter. Its nearest large neighbor, the Andromeda Galaxy, lies about 750,000 parsecs away, a little over 2.5 million light-years. Even the space between galaxies is not completely empty. It contains a faint haze of gas known as the intergalactic medium, so thin that only a few atoms drift through each cubic meter. Galaxies themselves form larger structures. They gather into small groups, massive clusters, and sprawling superclusters. The Milky Way and Andromeda are part of the local group, which belongs to the Virgo supercluster. Together with many others, they make up an even grander web of matter known as Laniakea, a vast region of interconnected galaxies stretching hundreds of millions of light years. Astronomers have cataloged millions of galaxies, though only a few are known by familiar names. Andromeda, the Magellanic Clouds, the Whirlpool, the Sombrero. Most are known only by catalog numbers, silent entries in humanity's growing map of the cosmos. People have wondered about the Milky Way for thousands of years. The Greek philosopher Democritus, living around 2,400 years ago, suggested that the pale band across the night sky was made of distant stars. Aristotle disagreed, thinking it was a glow from fiery vapors in Earth's upper air. Centuries later, the philosopher Olympiodorus reasoned that because the Milky Way looked the same from different places on Earth, it could not be part of the atmosphere at all. Scholars in the Islamic world took these questions further. The scientist Ibn al-Haytham, around the year 1000, tested whether the Milky Way showed parallax, a shift in position when viewed from different angles. Finding none, he concluded it must be far beyond Earth. Other thinkers, such as al-Biruni and Avicenna, described it as an immense collection of countless stars whose blended light formed a shining river across the heavens. Real proof arrived in 1610 when Galileo Galilei turned his telescope to the sky. Through the lens, the Milky Way resolved into a mist of innumerable faint stars. In 1750, Thomas Wright proposed that the Milky Way was a giant rotating disk held together by gravity. A few years later, Immanuel Kant expanded that idea, suggesting other similar island universes might exist beyond our own. In 1785, William Herschel tried to chart the Milky Way by counting stars, imagining the sun near its center in a flattened shape. By 1920, Jacobus Kapteyn described the galaxy as a small, lens-shaped system, while Harlow Shapley, studying globular clusters, proposed that the Milky Way was far larger and that the sun was nowhere near the center. Both were partly right, but had been misled by interstellar dust that dims distant starlight. In 1930, Robert Trumpler measured this effect and corrected the picture, revealing the Milky Way as a vast, disc-shaped galaxy with dark lanes of dust winding through its spiral arms. On a clear night, far from city lights, a patient observer can still see the Milky Way stretching across the sky, and even glimpse other galaxies with the naked eye. The Andromeda Galaxy, the large and small Magellanic Clouds, and the delicate Triangulum Galaxy shimmer faintly, reminders that our home is just one among billions of stellar cities scattered across the infinite dark. Over 1,000 years ago, in the 10th century, the Persian astronomer Abd al-Rahman al-Sufi looked to the sky and recorded one of the first known observations of the Andromeda Galaxy. In his book of fixed stars from the year 964, he described it as a small cloud, a faint and ghostly patch of light among the stars. He may also have mentioned the large Magellanic Cloud, calling it Al-Bakar, or the White Ox, following the naming of southern Arab astronomers. Yet the Magellanic Cloud lies nearly 70 degrees below the celestial equator, far beyond what al-Sufi could have seen from his home. Centuries later, when Ferdinand Magellan's ships crossed the southern seas, European sailors once again noticed this hazy glow hanging over the horizon, unaware that it was one of the nearest companion galaxies to our own. In 1612, the German astronomer Simon Marius independently observed the Andromeda Galaxy, and described it as a faint blur that filled his telescope's field of view. These early records helped anchor Andromeda's place among the mysterious nebulae that dotted the heavens. As human understanding expanded, philosophers began to imagine that these cloudy shapes might be entire systems of stars. In 1734, the Swedish thinker Emanuel Swedenborg proposed that the universe was filled with vast star systems, what he called world clusters, stretching far beyond human sight. His ideas, written in Principia, were astonishingly close to what modern astronomy would later confirm. A decade later, Pierre-Louis Maupertuis suggested that some of the soft patches of light seen in the sky were not isolated clouds, but immense gatherings of stars flattened by their spin, a concept inspired by earlier hints from Johannes Hevelius. Then, in 1750, the English philosopher Thomas Wright took a bold step further. He proposed that our Milky Way itself was a giant rotating disk made of countless stars held together by gravity. And perhaps, he suggested, those faint nebulae scattered across the night were other Milky Ways, entire galaxies of their own. By the late 18th century, this growing curiosity became a systematic effort to map the heavens. Charles Messier, hunting for comets, compiled a list of faint, cloudy objects that could be mistaken for them. His catalog contained 109 entries, including Andromeda and other nebulae. William Herschel later expanded this list to nearly 5,000 such objects, an extraordinary achievement for his time. In 1845, the Irish astronomer William Parsons, known as Lord Rosse, built a giant telescope and turned it toward one of Messier's entries, M51. What he saw stunned him, a spiral shape twisting outward like a cosmic whirlpool. It was the first time a human being had glimpsed the true structure of a galaxy. The early 20th century would finally reveal what these spirals truly were. In 1912, Vesto Slipher measured the light of spiral nebulae and discovered that many were racing away at enormous speeds. Their motion suggested that they were not small clouds within our galaxy, but distant systems far beyond it. In 1917, Heber Curtis observed a nova in the Great Andromeda Nebula, what we now know as the Andromeda Galaxy, and found it to be far dimmer than similar explosions inside the Milky Way. From this, he concluded that Andromeda must be vastly farther away, perhaps an island universe of its own. This daring idea sparked one of astronomy's most famous arguments, the Great Debate of 1920. Curtis and Harlow Shapley faced off over the true scale of the universe. Shapley believed the Milky Way was so large that it could contain all the nebulae, while Curtis insisted they were separate galaxies. Curtis pointed to dust lanes and velocity measurements as clues that Andromeda stood far outside our own galactic system. In 1922, the Estonian astronomer Ernst Öpik offered more evidence. Through careful mathematical reasoning, he showed that Andromeda lay well beyond the borders of the Milky Way. Then, in the mid-1920 seconds, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to settle the debate once and for all. He resolved individual stars in Andromeda and identified Cepheid variable stars whose brightness changes in a predictable way. Using them to calculate distance, Hubble proved that the spiral nebulae were indeed galaxies of their own, millions of light years away. In 1926, he introduced a classification system for galaxies by shape, a framework that astronomers still use today. As the 20th century unfolded, new technologies opened new windows on the universe. For centuries, Astronomy had relied solely on visible light, but dust clouds in space can block or scatter much of it. Infrared light, which travels at longer wavelengths, can slip through this dust and reveal what lies hidden within: the birthplaces of stars, the cores of galaxies, and the faintest objects at the edge of the observable universe. Because Earth's atmosphere absorbs much of this radiation, astronomers built telescopes on mountain peaks and eventually launched them into space, where they could observe unhindered. Then came radio astronomy. Radio waves pass freely through dust and gas, allowing astronomers to explore regions invisible to optical telescopes. These observations revealed enormous jets of energy erupting from galaxy cores and showed that the universe was far more dynamic than once imagined. Later, ultraviolet and X-ray astronomy added even higher energy views. Ultraviolet light revealed stars being torn apart by black holes, while X-rays mapped the glowing gas that fills galaxy clusters. Together, they revealed a striking truth. Nearly every large galaxy harbors a supermassive black hole at its center, a gravitational anchor millions or even billions of times heavier than the Sunday. In 1944, Dutch astronomer Hendrik van de Hulst predicted that hydrogen gas, the most abundant substance in the universe, should emit a faint radio signal at a wavelength of 21 centimeters. 7 years later, that signal was detected exactly as he described. This discovery revolutionized astronomy. Unlike ordinary light, 21-centimeter radiation can travel through dust almost unhindered. Using it, scientists mapped the motion of hydrogen gas throughout the Milky Way and discovered that its center contains a massive, rotating bar-shaped structure. In the 1,970 seconds, American astronomer Vera Rubin made an observation that changed everything again. Measuring how fast stars orbited their galactic centers, she found that galaxies were spinning far too quickly for the amount of visible matter they contained. Something unseen was adding gravitational pull, something invisible but immense. That mysterious substance became known as dark matter. By the 1,990 seconds, the Hubble Space Telescope was giving astronomers their sharpest view of the cosmos yet. From its position above Earth's atmosphere, Hubble confirmed that dark matter could not simply be explained by faint stars. Then came its most iconic achievement, the Hubble Deep Field. For days, the telescope stared at what seemed to be an empty patch of sky. When the image was complete, it revealed thousands of galaxies, each one an island of stars in the vast darkness. As more powerful instruments joined the search radio arrays, infrared observatories, and X-ray telescopes, astronomers began uncovering galaxies hidden behind the dense dust of the Milky Way. In a region once known as the zone of avoidance, whole new clusters emerged, invisible until then. And still, the numbers grew. In 2016, a team led by Christopher Consolis at the University of Nottingham analyzed deep space data and concluded that the observable universe may contain at least 2 trillion galaxies, 10 times more than those seen in Hubble's images. Yet even that staggering estimate may be incomplete. When NASA's New Horizons spacecraft, far from Earth's bright skies, measured the faint background glow of the universe, it found less light than expected. The findings suggested that there may be fewer galaxies than once thought, or perhaps that countless faint galaxies remain hidden beyond the limits of our vision, waiting for new generations of telescopes to bring them to light. Galaxies, the grand cities of stars scattered across the universe, come in 3 main forms: elliptical, spiral, and irregular. This broad system is often refined using the Hubble sequence, a classification scheme that arranges galaxies by shape. Yet this system elegant though it is, tells only part of the story. A galaxy's appearance doesn't always reveal how active it is, how fast it is forming new stars, or what is happening in its hidden heart where, in nearly every case, a supermassive black hole lies waiting. Even our own Milky Way has one, buried deep in its core, where gravity reigns supreme. Elliptical galaxies are the simplest to the eye. In the Hubble sequence, they're labeled from E0, almost perfectly round, to E7, elongated like a cosmic cigar. Viewed from any angle, they appear smooth and featureless, glowing softly with the light of old stars. These systems contain little gas or dust, and thus form few new stars. Their stellar populations are ancient, their orbits random, and their chemical makeup poor in heavy elements, evidence that their great burst of star formation ended billions of years ago. The largest ellipticals belong to a special class called CD galaxies, or supergiant ellipticals. Identified in 1964 by astronomer Thomas Matthews and his colleagues, these are the true monarchs of the cosmos, immense, luminous, and gravitationally dominant. A CD galaxy's bright core fades outward into a faint halo of stars that can stretch across millions of light years. Astronomers believe such giants grow by galactic cannibalism, the gradual merging of smaller galaxies within crowded clusters. Over billions of years, this process creates a single colossal galaxy surrounded by the debris of its devoured companions. The result is sometimes a fossil group, where one massive galaxy rules over a vast halo of hot, X-ray emitting gas, the last trace of countless collisions. A related but older idea, the cooling flow model, suggests that the hot gas filling a cluster can slowly cool and sink inward, forming new stars in the cluster's center. Evidence for this process has been found in the Perseus and Phoenix clusters, where bright knots of star birth glow amid the X-ray haze. Some elliptical galaxies also wear delicate stellar shells, concentric rings of stars rippling outward like waves on water. These form when a large galaxy swallows a smaller one, the collision creating gravitational waves that bunch stars into visible arcs. One of the most striking examples is NGC 3923, which displays more than 20 such shells. If ellipticals are the quiet old cities of the cosmos, spiral galaxies are the thriving metropolises. They gleam like cosmic pinwheels, their glowing arms curling outward from a bright central bulge. Though most of their visible mass lies in a flat disk of stars and gas, their true bulk is hidden within an enormous, dark matter halo that extends far beyond what we can see. The way spirals rotate, traced by the so-called universal rotation curve, is one of the strongest clues that dark matter exists at all. A typical spiral galaxy has three key components: a central bulge of ancient stars, a rotating disk where new stars and nebulae abound, and spiral arms, sweeping bands of starlight that trace waves of higher density moving through the disk. These arms are not fixed structures, but density waves, like slow traffic jams in space. Stars and gas drift in and out of them, bunching up temporarily as they orbit the galactic center. The compressed gas ignites star formation, making the arms shine brightly with hot, blue, newborn stars. In the Hubble system, spirals are labeled SA, SB, or C, depending on how tightly their arms are wound and how prominent their central bulge is. Say galaxies have tight, faint arms and large bulges. Say galaxies have loose, vivid arms and smaller centers. Some spirals appear fluffy and fragmented. These are called flocculent spirals, while others show perfect symmetry. The grand design spirals, like the Whirlpool Galaxy, whose arms sweep across space with elegant precision. Many spirals, including our own Milky Way, display a central bar of stars running through their core. These barred spirals, labeled SBA, SBB, or SBC, likely form when gravitational waves or tidal forces from neighboring galaxies redistribute the stars of the disk. Bars act as cosmic conveyors, funneling gas toward the center where it fuels both new star birth and the growth of supermassive black holes. The Milky Way is one such barred spiral, roughly 100,000 light-years wide and about 3,000 light-years thick, containing some 200 billion stars and weighing an estimated 600 billion solar masses. Astronomers have also identified rare superluminous spirals, titanic versions of ordinary spirals stretching up to 430,000 light-years across 5 times the size of the Milky Way. They blaze intensely in ultraviolet and infrared light, forming new stars at furious rates about 30 times faster than our galaxy. Not every galaxy fits neatly into the spiral elliptical divide. Some are peculiar galaxies, their shapes twisted by gravitational encounters. Among the strangest are ring galaxies, where a bright ring of stars and gas encircles a nearly empty core, often the result of a smaller galaxy plunging straight through the center of a larger spiral, leaving behind ripples that expand outward like shock waves. Even the Andromeda Galaxy shows ring-like patterns in infrared light, hinting that it, too, has suffered such collisions. Between ellipticals and spirals lie lenticular galaxies, labeled S0 in the Hubble system. They resemble spirals stripped bare, a central bulge, and a smooth disk, but no visible arms. If a bar crosses their center, they're called barred lenticulars, SB0. Lenticulars are thought to be transitional forms, spirals whose gas has been lost or consumed, leaving only an aging stellar population. Then there are the irregular galaxies, the misfits of the cosmos. They lack clear structure, often warped or fragmented by gravitational tug-of-war with larger neighbors. Some, called I retain hints of order. Others, too, are chaotic, torn apart by galactic encounters. The large and small Magellanic Clouds, our Milky Way's dwarf companions, are fine nearby examples. Astronomers have even discovered dark galaxies, ghostly systems with few stars but immense size, shining at barely 1% the brightness of the Milky Way. They may be relics that lost their star-forming gas early in their history, or never gathered enough matter to ignite widespread star birth. Whatever their origin, they offer vital clues to how dark matter shapes the universe. Despite the grandeur of giant spirals and ellipticals, the universe's most common residents are dwarf galaxies. These tiny systems are often just 1/100th the size of the Milky Way, containing a few million to a few billion stars. Some, known as blue compact dwarfs, sparkle with clusters of young, hot stars. Others are ultra-compact dwarfs, mere specks a few hundred light-years across, small enough to fit comfortably inside one of the Milky Way's star clusters. Many dwarf galaxies orbit larger hosts as satellites. The Milky Way has at least a dozen known companions, and perhaps hundreds more yet unseen. Studies of these dwarfs have revealed a striking pattern. Regardless of how many stars they contain, nearly all possess a central mass of about 10 million suns. This suggests that dwarf galaxies are overwhelmingly dominated by dark matter and that there may be a minimum scale below which galaxies cannot form, perhaps an intrinsic property of the dark matter particles themselves. Some scientists propose that this could hint at warm dark matter, a form that doesn't clump tightly on small scales, leaving the tiniest galaxies forever unborn. Galaxies are not lonely islands drifting through space. They are social, restless, and often collide or interact with one another in ways that reshape their structure and destiny. When two galaxies pass close by without fully colliding, their enormous gravitational forces pull at each other like invisible tides. The tug can twist spiral arms, warp disks, and even draw thin streams of gas and dust from one galaxy to the other. These near misses leave behind faint scars, distorted halos, elongated bridges of light, or faint streams of stars, signs of encounters that may last hundreds of millions of years. Sometimes, though, galaxies do not merely pass by, they collide head-on. Despite the drama of such events, the stars themselves almost never crash into one another, since the space between them is vast. Instead, it is the clouds of gas and dust that truly collide. When these dense clouds meet, they compress violently, triggering immense bursts of star formation. The result is a starburst galaxy, a temporary but spectacular flare of creation where thousands of stars are born at once. Collisions can also stretch galaxies into elongated tails, create bright rings, or even sculpt bar-shaped cores that spin like cosmic gyroscopes. When two galaxies approach too slowly to escape one another, gravity binds them together in a process called a galactic merger. Over time, they fuse into a single, larger system. If one galaxy is much bigger, the smaller one is torn apart and absorbed, a process astronomers aptly call galactic cannibalism. The Milky Way itself is guilty of this slow cosmic feast. It is currently consuming two small companions, the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy. Their scattered remnants now trail across the Milky Way's halo like faint celestial streams. Inside galaxies, new stars are born within cold molecular clouds, vast, dark regions of hydrogen and dust. In some galaxies, these clouds ignite at astonishing rates. These are the starburst galaxies, where stars form hundreds of times faster than in normal systems. A starburst typically lasts no more than about 10 million years, an instant on cosmic scales. Galaxies undergoing such frenzied activity glow brightly in ultraviolet and infrared light. Hot, massive stars ionize nearby gas, creating North-second regions, while the shock waves of dying supernovae compress surrounding clouds, triggering even more star formation. This chain reaction spreads like a ripple until the galaxy's gas supply runs out or is blown away by stellar winds. One famous example is M82, also known as the Cigar Galaxy, which flared into a starburst after a close brush with its neighbor, M81. Some galaxies also emit extraordinary amounts of energy at radio wavelengths. These are known as radio galaxies, and they rank among the universe's most powerful objects. Their gigantic lobes, regions glowing in radio light, are driven by jets of charged particles blasting out from the galaxy's core. Astronomers classify them using the Fanneroff-Rayleigh system. FR1 galaxies have dimmer, elongated lobes, while FR2 galaxies shine with brilliant hotspots at their edges. The most extreme examples are giant radio galaxies, whose lobes can stretch across millions of light years. One of the largest known is Alcyonius, whose radio structures span more than 16 million light years. Another, 3C236, is only slightly smaller, These vast lobes are powered by supermassive black holes at their centers, hurling out matter at nearly the speed of light. When the central black hole of a galaxy becomes highly active, swallowing gas and dust at a furious rate, the galaxy is called active. Its energy dominated by an active galactic nucleus, or AGN. In these objects, an accretion disk of infalling matter swirls around the black hole. As the gas spirals inward, friction and gravity convert its energy into radiation so intense that it can outshine the rest of the galaxy. Around 10% of AGNs also produce relativistic jets, thin beams of plasma ejected from the poles at near light speed. Though astronomers have studied these phenomena for decades, the exact process that forms such jets remains one of astrophysics' enduring mysteries. Among the many kinds of active galaxies, Seyfert galaxies and quasars are the most famous. Seyferts appear much like ordinary galaxies, but their cores blaze with exceptional brightness. They are divided into two main types based on the light they emit, some showing narrow spectral lines, others broad. Quasars, by contrast, are so luminous that they were first mistaken for stars, appearing as bright points rather than extended shapes. They can outshine entire galaxies, radiating hundreds of times the light of the Milky Way. The nearest known quasar, Markarian 231, lies nearly 600 million light-years away, while others, like UHZ-1, observed at a distance of about 13 billion light-years, date back to when the universe was still young. Quasars also helped reveal one of the strangest effects predicted by Einstein's general theory of relativity: gravitational lensing. When the light from a distant quasar passes near a massive galaxy, the galaxy's gravity bends and magnifies it, acting like a natural cosmic telescope. Some quasars even appear as multiple images or bright arcs, their light split and distorted by the gravity of intervening galaxies. A related and even more extreme class of active galaxies are the blazars, where one of the high-speed jets points almost directly toward Earth, making their radiation appear even more intense. The difference between quasars, Seyferts, radio galaxies, and blazars is largely one of perspective. In the unified model of active galaxies, they are essentially the same type of object seen from different viewing angles and surrounded by varying amounts of obscuring dust and gas. Another intriguing category is the LINER, short for Low Ionization Nuclear Emission Line region. In these galaxies, the light from the core shows only weak ionization atoms, stripped of relatively few electrons. Liners may be powered by modestly active black holes, shock waves, or the fading energy of aging stars. Surprisingly, nearly 1/3 of all nearby galaxies appear to have liner-type nuclei, making them one of the most common forms of low-level galactic activity. Closely related are the luminous infrared galaxies, or LIRGs, which blaze most brightly not in visible light, but in the infrared. A typical LIRG radiates more than 100 billion times the energy of the sun, its glow coming from dust heated by swarms of young stars and sometimes by a hidden active nucleus. To reach that level of luminosity, such a galaxy must create new stars at a rate of about 18 solar masses each year. Even more extreme are the ultraluminous infrared galaxies, or ULIRGs, whose energy output exceeds that of LIRGs by more than a factor of 10, and whose star formation rates can top 180 solar masses per year. Many of these luminous galaxies are caught in the act of merging, their interactions driving gas toward their centers, where it fuels both new stars and black holes. Infrared galaxies are remarkable because most of their power emerges at wavelengths between 60 and 100 microns, far beyond the visible range. In the early universe, such objects were far more common than they are today, marking a time when galaxy mergers and starbursts were far more frequent. Modern observatories that detect infrared light, like the James Webb Space Telescope, continue to uncover these hidden powerhouses, revealing the dusty, energetic past of the cosmos. Measuring the true size of any galaxy is far from simple. Galaxies do not have clear boundaries. Their starlight gradually fades into the darkness. Astronomers instead use statistical methods tracing the brightness, gas density, or rotation of stars to estimate their dimensions. Each galaxy, whether small and irregular or vast and luminous, carries its own signature of growth, collision, and change. Through these interactions, gentle or violent, the universe continues its long and intricate dance of creation, destruction, and renewal. In the early decades of the 20th century, astronomers were still learning how to describe the shapes and sizes of galaxies in consistent terms. In 1936, Edwin Hubble made one of the first attempts to measure galaxy diameters. He used a simple approach, combining the apparent angle a galaxy covered in the sky with its estimated distance. The result was called the angular diameter, or sometimes the metric diameter, a useful but imperfect tool since galaxies have no clear edges. A more refined method appeared later, the isophotile diameter, which defines a galaxy's size not by where it visually ends, but by how bright it appears. An isophody is a contour line connecting points of equal brightness in an image, like a topographic map drawn in light instead of height. Astronomers measure brightness in magnitudes per square arcsecond, describing how much light falls across a small patch of sky. The central region of a typical spiral galaxy might glow at about 18 magnitudes per square arcsecond, roughly the brightness of an 18th magnitude star spread evenly over that area. Using this method, astronomers often define the outer boundary of a galaxy at a surface brightness of 25 magnitudes per square arcsecond in the blue region of light, the so-called D25 standard. Another common measurement is the half-light radius, or effective radius, written as R. This is the distance from the center that encloses half of the galaxy's total light. The idea was introduced in 1948 by Gérard de Vaucouleurs, and though the choice of 50% was somewhat arbitrary, it turned out to be immensely practical. Later, astronomers such as Robert Fish and José Luis Cercic expanded on the concept, linking galaxy brightness and mass to their effective radii. To measure a galaxy's total brightness accurately, scientists developed mathematical models of its light profile. In 1976, the Armenian-American astronomer Vae Petrosian introduced what became known as the Petrosian method, a new way of determining a galaxy's size by comparing its local brightness to the average brightness over a larger area. If the local brightness drops to a specific fraction of the average, that point defines the Petrosian radius. The Sloan Digital Sky Survey, SDSS, later adopted a refined version of this technique, using light in the red part of the visible spectrum, around 658 nanometers. The Petrosian approach has a key advantage. It is relatively independent of distance and redshift, meaning that galaxies farther away can be measured with the same standard as nearby ones. For galaxies whose brightness fades smoothly from the center, the Petrosian radius captures nearly all their light. For more concentrated systems, like elliptical galaxies, it captures about 80%. The method is not perfect. It can miss faint light at the edges or introduce small errors compared to the older isophotile approach, but it remains a robust way to compare galaxies across the universe. To account for these limitations, astronomers in 2005 proposed a correction based on Sérzich's law, which describes how a galaxy's brightness falls off from the center. This modified form is used in major near-infrared surveys such as the 2-micron all-sky survey. Operating at wavelengths around 2.2 micrometers, 2MASS detects older, cooler stars, invisible to optical instruments. In this system, a galaxy's edge is defined where the surface brightness in the near-infrared K-band drops to 20 magnitudes per square arcsecond. Scientists also use several types of apertures: circular, isophotral, or Cron apertures, which extend about 2.5 times the radius containing the first moment of a galaxy's light, to capture its total emission. As astronomers refine these measurements, they also came to understand that galaxies rarely exist alone. Most belong to groups or clusters, bound together by mutual gravity. Truly isolated galaxies, those that have avoided major interactions for billions of years, are surprisingly rare, making up perhaps 5% of all known systems. Even these loners often have smaller satellite galaxies orbiting them, or faint trails of stars left from past mergers. Within these gatherings, gravity works against the overall expansion of the universe. On the largest scales, space itself stretches, driving galaxies apart according to Hubble's law. Yet within clusters, gravity holds them together in local pockets of stability. These clusters formed early in cosmic history, as dense concentrations of dark matter pulled galaxies into vast swarms. Smaller groups merged into larger ones, heating the surrounding gas to extraordinary temperatures tens of millions of degrees Kelvin. Today, a typical galaxy cluster contains 70–80% dark matter, 10–30% hot gas, and only a few percent in the galaxies we can see. Clusters come in many sizes. The smallest, called groups, often hold a few dozen galaxies, moving relatively slowly, allowing them to remain gravitationally bound. These groups are the most common environments for galaxies and contain most of the universe's ordinary matter. Larger clusters may include hundreds or thousands of galaxies and are often dominated by a single massive elliptical at their center, known as a brightest cluster galaxy. This giant grows by tidally absorbing its smaller companions, feeding off the gravitational chaos around it. Beyond clusters lie superclusters, sprawling regions containing tens of thousands of galaxies, arranged in webs of groups and filaments. These filaments stretch around enormous voids, cosmic bubbles nearly empty of matter. Together they form the cosmic web, the vast scaffolding of the universe. On scales beyond that, space begins to appear uniform in all directions, though recent discoveries challenge that notion. One of the most immense known structures, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years, making it the largest single feature ever detected. Our own Milky Way belongs to a modest neighborhood called the Local Group, spanning roughly 1 million parsecs across. It includes more than 50 galaxies, dominated by the Milky Way and the Andromeda Galaxy, with numerous dwarf galaxies orbiting both. The Local Group itself sits within the Virgo supercluster, centered on the massive Virgo cluster, and that entire structure is part of an even greater complex called the Laniakea supercluster, a gravitational basin containing around 100,000 galaxies bound together by the slow, ancient dance of dark matter and gravity. Beyond their stars and gas, galaxies possess another, less visible component: magnetic fields. These fields weave through the interstellar medium like unseen threads, influencing the flow of gas and dust. In spiral galaxies, magnetic lines follow the graceful curves of the arms, guiding the motion of charged particles and helping regulate the transfer of angular momentum. This transfer is crucial. It allows gas clouds to collapse inward, forming dense knots where new stars are born. Though invisible to our eyes, these magnetic fields play a quiet but vital role in shaping the rhythm of galactic evolution, linking the smallest scales of star birth to the grandest motions of the cosmic web. Magnetic fields weave silently through galaxies, shaping their structure and influencing their evolution in ways that are only now beginning to be understood. In most spiral galaxies, the average magnetic field measures about 10 microgauss, roughly 1 nanotesla. By comparison, Earth's magnetic field is tens of thousands of times stronger, averaging about 30 microteslas. Some nearby galaxies, such as Andromeda M31 and Triangulum M33, possess weaker fields of around 5 microgauss, while more active, gas-rich galaxies like M51, the Whirlpool Galaxy M83, and NGC 6946 can reach around 15 microgauss. Within the bright spiral arms, where cold gas and dust collect, these fields intensify to as much as 25 microgauss. The strongest known galactic magnetic fields between 50 and 100 microgauss are found in starburst galaxies such as M82 and the Antennae galaxies, as well as in the central star-forming regions of barred spirals like NGC 1097. These extreme environments reveal how magnetic energy, turbulence, and star formation are deeply intertwined in galactic ecosystems. Modern theories of galaxy formation are built on a framework known as lambda-cold dark matter, or LCDM. This model describes how structure in the universe grew from the earliest fluctuations after the Big Bang. Around 300,000 years after that moment of creation, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, a transition called recombination. For the first time, light could travel freely through space, marking the end of the Dark Ages. At that time, there were no stars, only a nearly uniform sea of hydrogen, helium, and dark matter. Tiny irregularities in the density of this early material slowly amplified under the pull of gravity. Within halos of dark matter, ordinary gas, what scientists call baryonic matter, began to collect and compress, forming the first proto-galaxies. As the gas collapsed, it heated up, and for stars to form, it had to cool by radiating energy away. Because hydrogen and helium are poor radiators of heat, this process was slow. Gradually, though, these primitive clouds spun up into rotating disks, and regions dense enough for star formation began to appear. The first generation of stars, known as population 3 stars, contained almost no elements heavier than helium. They were massive, short-lived, and incredibly bright, producing intense ultraviolet radiation that ionized surrounding hydrogen gas. These stars created expanding bubbles of ionized plasma, and as they died in supernova explosions, they scattered newly forged elements, carbon, oxygen, and iron into the surrounding space. The birth and death of these first stars ended the Dark Ages and began the long process of reionization, when ultraviolet light from young galaxies made the universe transparent once again. The heavy elements expelled by these first supernovae enriched later generations of stars, known as population 2 stars. Over time, galaxies became chemically richer, setting the stage for population I stars like our Sun, which contain abundant heavy elements. As telescopes improved, astronomers refined theoretical models of this early period using detailed spectroscopic and photometric data from distant galaxies. Observations from the James Webb Space Telescope have pushed this frontier further than ever before. Some early reports from JWST suggested galaxies at redshifts as high as 16, meaning they existed when the universe was only a few 100 million years old. Later analyses adjusted some of these values downward, but even so, Webb has confirmed that complex galaxies already existed surprisingly soon after the Big Bang. Detecting individual population 3 stars remains elusive. For example, certain emission lines once thought to mark their presence, like helium-2 radiation in the Cosmos Redshift 7 galaxy, were later found to include traces of oxygen, evidence that the system had already been enriched by earlier generations of stars. Each discovery helps refine the timeline of how the first galaxies formed and evolved. Once star formation began, the process of galaxy assembly became extremely complex. Radiation, gas pressure, and gravity interacted in a delicate balance. Within roughly 1 billion years, the essential structures of a young galaxy began to emerge: globular clusters, a central bulge, and often a supermassive black hole anchoring the core. The black hole's intense energy release helped regulate how fast the galaxy could grow, preventing unchecked collapse. During this early phase, galaxies experienced enormous bursts of star formation, producing the brilliant, blue, irregular shapes that telescopes now see at great distances. Over the next few billion years, these turbulent systems settled. Matter cooled and organized itself into rotating galactic disks. Meanwhile, galaxies continued to accrete new material, cold gas clouds, and small dwarf galaxies that fell inward from the surrounding dark matter halo. These mergers provided fresh fuel for new stars and slowly built up the heavy elements that later allowed planets to form. Even now, galaxies continue to grow through such accretion and minor mergers. Star formation rates vary widely depending on environment. Void galaxies, isolated in vast cosmic gaps, tend to have the highest star formation efficiency for their mass. Field galaxies, like many spirals, including our own, show moderate activity. In crowded clusters, where galaxies are stripped of their gas by interactions and hot plasma, star formation drops sharply. Collisions and mergers remain the most powerful agents of change. In the early universe, these encounters were frequent, giving rise to chaotic, oddly shaped galaxies like NGC 4676, the Mice galaxies, and the Tangled Antennae galaxies, both vivid examples of tidal disruption. During such events, gas and dust are pulled into long, glowing tidal tails, while the stars themselves mostly glide past each other unharmed. Our own Milky Way is currently drifting toward the Andromeda Galaxy at about 130 kilometers per second. In roughly 5 to 6 billion years, the two will collide and merge, forming a single, giant, elliptical system. While this sounds catastrophic, the vast emptiness between stars means few, if any, direct stellar collisions will occur. Instead, both galaxies will simply blend, their shapes and orbits transformed by gravity's slow choreography. Evidence from computer simulations suggests that around 11 billion years ago, the Milky Way experienced a major merger with a large galaxy nicknamed the Kraken, an event that may have helped shape its thick disk and halo. Since then, the rate of such giant collisions has declined. The modern universe is calmer. Most large galaxies have remained relatively stable for billions of years. The overall cosmic star formation rate, the pace at which the universe creates new stars, likely peaked about 10 billion years ago, during an era when galaxies were young, active, and full of gas. Since then, star formation has slowed, and the universe has entered a quieter, more mature phase. Yet even now, across the dark fabric of space, the same ancient forces continue their patient work. Gravity drawing, gas cooling, and light kindling anew in the endless cycle of galactic creation. The universe is crowded with stars, and many of them likely host their own systems of worlds. For most of human history, other planets were the realm of stories. We could see only the bodies in our own solar system and imagine the rest. That changed as instruments improved. Bit by bit, the idea of other Earths moved from wishful thinking to careful measurement, and a new field exoplanet research took shape. Exoplanets are planets that orbit stars beyond the Sunday. They are hard to spot because they do not shine by themselves. They reflect starlight or give off faint heat that is drowned out by the star they orbit. The first confirmed exoplanets were found in 1992, and they broke every expectation. They circled a pulsar, the spinning remnant of a dead star. Planets around such a harsh, exotic object showed that nature can build worlds in places we never expected. In 1995, astronomers found 51 Pegasi b, the first planet around a normal, sun-like star. That discovery opened the floodgates. Since then, the number of known planets has risen into the thousands, and the basic idea has held. Planets are common. Finding these worlds is difficult, so astronomers use clever, indirect methods. One major tool is the radial velocity, or Doppler method. A planet's gravity makes its star wobble slightly, as both orbit a shared center of mass. When the star moves toward us, its light is shifted to bluer wavelengths. When it moves away, the light is shifted to redder ones. By tracking this pattern, scientists can infer a planet's presence, estimate its mass, and learn about the shape and speed of its orbit. Another very productive method is the transit technique. If the orbit lines up just right, a planet crosses in front of its star from our point of view, causing a tiny, repeatable dip in starlight. The depth and duration of that dip reveal the planet's size and orbit, and in some cases, the way starlight filters through the planet's atmosphere can hint at the gases present there. The Kepler Space Telescope, launched in 2009, watched more than 150,000 stars at once and used this approach to great effect. Kepler showed that planets come in many sizes, and that compact, tightly packed systems are common. Exoplanets are astonishingly diverse. Some are gas giants rich in hydrogen and helium, like Jupiter and Saturn. Others are terrestrial worlds with rock and metal, like Earth and Mars. There are ice giants, similar to Uranus and Neptune, whose layers include water, ammonia, and methane ices. Beyond these familiar types, we have found stranger classes, hot Jupiters, that skim so close to their stars that their day sides can heat to thousands of degrees. Planets on eccentric orbits that swing between deep freeze and blistering heat, and even rogue planets that drift through interstellar space without any host star at all. Understanding these worlds requires asking how planets form. The story begins in a molecular cloud, a huge, cold region of gas and dust. Under gravity, A cloud fragments and collapses. The center forms a protostar, and around it spreads a flat protoplanetary disk, the birthplace of planets. Inside the disk, grains of dust collide and stick. Small clumps grow into planetesimals, then into protoplanets. Gravity helps these bodies attract more material. This gradual buildup is called core accretion, and it is the main path for building rocky planets and the solid cores of gas giants. In some cases, parts of a massive disk may collapse quickly under their own gravity disk instability, which could create giant planets on short timescales and may explain some hot Jupiters. Where a planet forms in the disk matters. Close to the star, heat drives off volatile ices, leaving rock and metal to build rocky worlds. Farther out, temperatures fall. Ices can condense, adding extra material to the cores. Once those cores get large enough, they can pull in deep envelopes of hydrogen and helium, making gas giants. After planets form, they do not always stay put. Interactions with the gas disk and with other planets can cause migration. Giants can drift inward toward the star. Smaller worlds can be scattered into wide, tilted, or eccentric orbits. The result is a surprising variety of architectures, many unlike our solar system. The study of exoplanets naturally leads to the question of habitability. Scientists often start with the habitable zone, the range of distances where a planet's surface could allow liquid water. Water is central to life as we know it, but life on Earth has proven adaptable. Extremophiles survive in boiling springs, acidic lakes, and polar ice. That suggests that the real range of habitable conditions may be wider than the simple picture of a mild, Earth-like world. Many exoplanets have been found inside their stars' habitable zones, but they remain too distant for detailed surface studies. Even so, we can begin to probe their atmospheres. When a planet transits, starlight passing through its thin air can carry the signatures of gases, combinations of oxygen, methane, and other molecules' biosignatures might hint at biological activity if found together in certain ratios. New observatories, including the James Webb Space Telescope, launched in 2021, are designed to take spectra of transiting planets and look for such chemical fingerprints. These early steps do not prove life, but they tell us whether a world's air is friendly to liquid water and complex chemistry. The discovery of multi-planet systems has deepened the picture. Many stars host several planets, sometimes arranged in neat, orderly chains where orbits line up in resonances, simple ratios like 2:1 or 3:2. Some systems have small, rocky planets close in, with giants farther out, a layout that echoes our own. Others place large planets in tight, hot orbits, or pack many worlds inside distances smaller than Mercury's path. These differences show that planet formation is flexible. Small changes in the disk's mass, chemistry, and temperature, or in the timing of migration, can lead to very different outcomes. Each detection method adds a piece to this puzzle. Radial velocity finds heavier planets and can work for many types of stars. Transits find planets that line up just so and excel at measuring size. When both methods apply to the same planet, we can combine size and mass to estimate density, telling us whether a world is likely rocky, gassy, or something in between. In special cases, direct imaging can separate a faint planet's light from its star's glare, though this works best for young, massive planets far from their stars. Other techniques like watching a star's light bend during a gravitational microlensing event can catch planets that would be missed by most other methods. As the catalog grows, patterns emerge. Small planets between Earth and Neptune in size, often called super-Earths and mini-Neptunes, appear to be common, even though our solar system has none. Hot Jupiters are easier to find and were among the first discoveries, but they are less common than smaller worlds. Planets also seem plentiful around many kinds of stars, from sun-like stars down to smaller, cooler red dwarfs. In short, our solar system is one outcome among many. All of this points to a simple, profound idea. Planet making is a natural part of star making. When a star forms, a disk forms with it. Dust and gas in that disk almost inevitably assemble into planets of many kinds. Over time, collisions, migration, and chemistry sculpt each system into its own shape. Some will be quiet and stable, others will be wild and chaotic. Some may offer calm, long-lived conditions where water can persist and chemistry can grow more complex. We are still at the beginning. The first exoplanets were confirmed only a few decades ago, and already we have moved from simple detection to the characterization of atmospheres and climates. We now watch for the faintest shadows, the smallest wobbles, and the most delicate hints of air and cloud on worlds we cannot see directly. Every method has limits and pitfalls, so claims are checked and checked again. As instruments improve and surveys continue, the picture sharpens. Planets are everywhere. Their stories are varied, and among those stories may be worlds where the conditions we value, liquid water, a stable sky, gentle sunlight, have had time to work their slow magic. In exoplanet science, progress has moved at a breathtaking pace. In 1995, when 51 Pegasi b was announced, only a handful of planets were known beyond our solar system. Now there are thousands of confirmed worlds and many more candidates waiting to be checked. This flood of data has widened our view of what a planetary system can be and pushed theory to keep up. Old assumptions have fallen away. Planets come in sizes, orbits, and compositions that earlier models did not expect, and new ideas have been built to explain them. Comparing this rich variety with our own neighborhood sharpens our sense of how many things had to line up for Earth to be what it is. Distance from the sun, a stabilizing moon, a protective magnetic field, and a careful blend of elements. All of these helped make a surface where oceans could last and life could take hold. Looking outward reminds us that such conditions can be rare in detail, yet it also hints that habitable settings may be common in number. Across the galaxy, there may be many just right places, each with its own path to chemistry and, perhaps, biology very different from ours. Astronomers are also drawn to what these worlds are like on the inside and at the surface. Some planets likely wear thick, crushing blankets of carbon dioxide, trapping heat in a runaway greenhouse. Others hold only thin, fragile air. There may be oceans hidden under ice, sealed away but active with chemistry. Some planets may be reshaped again and again by volcanoes, their air renewed by eruptions. Each of these settings tells us something about how planets grow, cool, and change over time. To probe those conditions, scientists use spectroscopy to study starlight that has interacted with a planet's atmosphere. Signatures of water vapor, carbon dioxide, methane, sodium, and other molecules allow estimates of temperature, pressure, and composition. Step by step, such measurements turn dim points of light into places with weather, clouds, and histories. They also guide the hunt for habitability by pointing to atmospheres that could support liquid water or preserve fragile molecules. The life of a planet is tied to the life of its star. Young stars are noisy neighbors. They flare, blast out strong winds, and flood nearby space with radiation that can strip atmospheres or choke off planet building. As stars age and swell into red giants, their light and size change dramatically. Inner worlds can be scorched or swallowed. Outer worlds can thaw or freeze in new ways. When a star sheds its outer layers and becomes a white dwarf, it alters its system again. These changes show why exoplanet studies must include the whole stellar environment. Planets and stars evolve together. On a larger scale, exoplanet surveys connect to the story of the Milky Way. By sampling different regions, dense clusters, metal-rich neighborhoods, and high radiation zones, astronomers see how planet types shift with stellar age, chemistry, and setting. Patterns emerge. How heavy elements affect planet building, how crowded regions may disrupt or rearrange orbits, how calm, isolated areas can nurture long-lived systems. From these comparisons, a broader picture grows, linking planet formation to the galaxy's history of star birth and chemical change. All of this rests on technology. Sensitive detectors, ultra-stable spectrographs, space-based observatories, and powerful data tools have turned exoplanet hunting from a hope into a mature science. The Transiting Exoplanet Survey satellite, launched in 2018, scans most of the sky for planets that cross their stars, focusing on nearby, bright targets that are easier to study in detail. On the ground, telescopes with adaptive optics cancel out the blur of Earth's atmosphere. With these tools, astronomers have even directly imaged a few massive planets and begun to analyze their light. Despite all this progress, there are deep mysteries left to solve. Why do hot Jupiters appear in so many systems but not in ours? What sets the balance between rocky worlds and gas giants? Which roles do stellar metallicity, magnetic fields, and early disk conditions play? Why do some systems settle into neat, orderly layers, while others end up with tilted, eccentric orbits and close gravitational resonances? Each new planet found adds a clue, but it also raises new questions. Models grow more sophisticated, observing strategies become sharper. The cycle continues. The arc of the field from the first pulsar planets in 1992 to the thousands of worlds known today reflects a simple drive to understand our place in the cosmos. Every exoplanet is a test case for the physics of disks, dust, gravity, and chemistry. Some push those rules to their limits. Worlds with blazing daysides and iron-rich skies, planets with exotic mixes of rock and ice, bodies that may hide salty seas beneath frozen shells. The future likely holds. Even stranger finds worlds with extreme climates, rare elements, and, perhaps, signs of life. Exoplanets also reshape how we think. They show that the same laws can lead to wildly different outcomes. Tiny, rocky worlds, massive gas spheres, quiet circular orbits, chaotic elliptical paths. Nature tries all the options. As the mosaic fills in, we see not just the mechanisms of planet building, but also the ties between stars, planets, and the conditions that might allow life. In learning about distant systems, we see our own more clearly, the delicate balances that keep oceans stable, the long rhythms that shape climate, and the fragility that makes our world precious. Even as instruments improve, the most important engine of discovery remains curiosity. How common are Earth-sized planets with calm, protective atmospheres? Could life exist in forms that do not match our expectations? How do planetary systems change over billions of years? And how often do they find stable ground. Each answer opens a door to more questions, and each new observation gives a brief look at the processes that shaped both faraway worlds and our own. Exoplanet science is, at heart, a story about the universe learning to look at itself with greater focus. It is not only a catalog of planets, it is a record of how matter organizes into families, how energy flows through air and ocean, and how time writes landscapes across rock and ice. As telescopes grow more powerful, detection methods more precise, and theories more refined, the next chapters will likely surprise us again, with planets stranger, subtler, and more beautiful than we have yet imagined. Each one will be another small light in a vast field of stars, and another reminder that the cosmos is generous with possibilities,